In this video, we focus on solving two variable LPs, and in particular we'll solve such LPs graphically. Because there are only two variables involved, we can plot the feasible region of such an LP on the plane, and we can easily find the solution graphically. Alright, our working example is the heavenly pouch problem that we formulated earlier. In this model, we are looking at manufacturing two types of carriers, the non-reversible carrier and the reversible carrier. So we manufacture X1 units of non-reversible and X2 units of the reversible carrier. So we make $15 of profit per unit of non-reversible carrier and $25 of profit per unit of the reversible carrier. Then we have several resource constraints. The resources we are using to manufacture these slings are the solid color fabric, then we have the printed fabric that is used for the reversible carrier, and then we also have the manufacturing budget. So we outsource the manufacturing process and we have a limited amount of money to spend on manufacturing costs. Finally, we have a demand constraint that tells us that no more than 350 units of the non-reversible carriers can be sold. And we have the non-negativity constraints, of course. Alright, so how do we solve this graphically? What we need to do is to plot all the constraints on the plane. Because there are only two variables, this can be easily done. So what we'll do, we'll plot a line corresponding to the first constraint, which will be x1 plus x2 is equal to 450. Then this line will split the plane into two parts, and the feasible points with respect to this constraint will belong to one of the half planes that this line defines. And we'll do the same for all the remaining constraints, and then our feasible region will be the intersection of all of these half planes defined by all the lines corresponding to the constraints. Okay, so let's see how things look like for this example. So we have four constraints other than non-negativity, and these four plots here show the corresponding half planes that these constraints define. So for example, this plot here shows the set of points that satisfy the constraint x1 plus x2 is less than or equal to 450. So this set of points is shown in yellow. So as we can see, the line where x1 plus x2 is equal to 450 splits this plane into two half planes, and one of these half planes will contain the points that are feasible with respect to this constraint. So for example, if we plug in the point of the origin, x1 and x2 are equal to 0, and clearly this is less than 450, so clearly this will be the half plane that will correspond to the points for which x1 plus x2 is less than or equal to 450. Alternatively, we could easily determine which of the two half planes correspond to the feasible points by looking at the direction of the gradient vector for this function here on the left hand side. So we have a function x1 plus x2. The gradient would be the vector 1, 1, and the vector 1, 1 points in this direction right here, right? So, and the gradient vector points in the direction of the function increase. So the function is equal to 450 at this line right here, and direction of increase is this way. So therefore, if we move in this direction, the corresponding points will have x1 plus x2 greater than 450. And for feasibility, we need it to be less than or equal to 450. So therefore, the opposite side of the line will correspond to the points that are feasible with respect to this constraint. Similarly, we build all the other half planes corresponding to the feasible points with respect to each constraint. For example, for x2 less than or equal to 300, this line is parallel to the x1 axis, and clearly the feasible points with respect to this constraint will be below this line. All right, so then we have the budget constraint. Again, the yellow points here are the points that satisfy this constraint. The demand constraint tells us that x1 is less than or equal to 350, and these are the points that are feasible with respect to this constraint. And finally, the last plot here shows the set of points where x1 and x2 are non-negative. All right, so now to find the points that are feasible with respect to all the constraints, we need to find the overlap of all these yellow regions, and the set of points that satisfy all of these constraints will be the feasible points. Therefore, the set of points in the overlap of all these yellow regions will give us the feasible set for our LP. So let's see how it looks like. So this is the overlap. We can see all the 4 constraints and the non-negativity are shown here. So this is the set of all the feasible points for our LP. All right, so and here it is in a better resolution. We can find the points of intersections of different lines easily by just writing down the corresponding system of equations with inequalities replaced by the equalities. For example, if you want to find the intersection of the solid fabric constraint with the budget constraint, then we need to write down the system of 2 equations. x1 plus x2 is equal to 450, and 4x1 plus 5x2 is equal to 2000. And similarly, we can find the coordinates of all the corner points here easily. So why are the corner points important? Because as we will soon see, these are the points where we should look for the optimal solutions. All right, speaking of which, how should we determine the point that is optimal here? Or maybe there are more than one optimal points. How do we know? Obviously, we need to look at the objective for this, right? So this is just a feasible region, but we also need to pay attention to the objective. And the objective was 15 times x1 plus 25 times x2. So let's plot the objective function for a particular value of the objective that we want to select. So let's say we may think of some arbitrary level of profit that we want to target, some realistic level of profit. So let's think of 3000, right? So let's set the objective z to 3000. So essentially we'll say, okay, our objective, which is z, is equal to 15 times x1 plus 25 times x2, and this is equal to 3000. So I just want to see how the set of points where my profit will be equal to 3000 look like within the feasible region. All right, so then what we do, we draw the line where 15 times x1 plus 25 times x2 is equal to 3000, and this is the line. And to draw the line, all we need is just to take 2 points. So for example, I can set x1 to 0, and then we can see that if x1 is equal to 0, then x2 is given by 3000 divided by 25, which is 120. So 1 point is 0, 120, and then if I set x2 to 0, then 15 times x1 equal to 3000 gives me x1 equal to 200, so 200 and 0 is the second point. So we have this line passing through these 2 points, and for all the points in this line segment between these 2 points, the objective value is equal to 3000, and all these points are within the feasible region because they're in yellow, right? So, and the yellow color shows here all the feasible points. Therefore, we can see that we can easily reach the objective of 3000 in any of these points. So there are infinitely many solutions that satisfy 15 times x1 plus 25 times x2 is equal to 3000. And we call the set of points for which the profit level is the same, we call this the isoprofit line. So the isoprofit line would be the line where the profit level is the same for every point on the line. All right. So ISO means the same in translation from Greek, and ISO profit line would be the line where the profit is the same, the line that corresponds to the same level of profit. Okay. In case of a minimization problem, we would call it the ISO cost line, because typically a minimization objective is something that we call a cost function. So ISO cost line would be in a minimization case. So let me write it down here, ISO cost line. We see that this ISO profit line at the level of 3000s gives us a bunch of feasible points. We raise our appetites and we say, okay, why don't we raise our target profit maybe by 100%, and why not try the profit of 6000s and see if we get feasible solutions for that. Okay, so I double this right hand side here and draw the ISO profit line for the level of profit of 6000s. So now we get this line right here, and we can see that we still make this target profit in many points within the feasible region. So the target profit of 6000s is clearly still feasible for us, and we can keep increasing that level. And you know, when you look at the plots for these ISO profit lines, because we only changed the right hand side here and we didn't change the coefficients for the variables x1 and x2, the slope of the line doesn't change. So we are moving essentially this line on parallel to the original ISO profit line that we drew here. And we can see that when we increase the profit level, the ISO profit line moves in this direction right here. And this direction is actually the direction of the gradient for our cost function, or the profit function actually in this case, because we maximize. So the profit function is 15 times x1 plus 25 times x2. So our gradient vector is given by 15, 25, and it points in this direction here. So this is your direction of increase. And when you move in this direction, your profit keeps increasing. And of course, you would want to increase it infinitely, but that would be too good to be true. And we can clearly see that, let's say, if I try to increase it to, let's say, $10,000, then my ISO profit line will be somewhere outside of the feasible region. If we show the ISO profit line with this dashed line right here, so when we keep increasing the profit, what is happening, this line is gonna move up and up and up. So we can see that we still stay within the yellow region for some of the points of this line, which means that we still have the feasible points for this target profit that corresponds to the level of this ISO profit line. And then eventually we reach this point here in the corner, after which we are not going to have any more overlap with the feasible region if we keep pushing the profit level up. So for example, if I set my target to be something like $10,000, then clearly I'm gonna be outside of the feasible region. All right, so there will be no feasible schedule which will allow me to reach that target profit level. So this leads us to the conclusion that this point x star on the plot is going to be the point that corresponds to the highest profit that I can achieve within this feasible region. Again, you know, if I try to increase the profit further, then I would be immediately outside of the feasible region. I wouldn't have any overlap with the feasible region for my ISO profit line if I was too optimistic about the profit level that I'm targeting. So we come to the conclusion that this x star is the optimal point, and now we just need to find the coordinates for x star to find out what the optimal solution is to our problem. Okay, so this point x star, from the plot we can clearly see that it lies on the intersection of the two constraints. The first constraint is the printed fabric constraint that corresponds to x2 equal to 300. So this line is where x2 is equal to 300, but the printed fabric constraint is, of course, x2 is less than or equal to 300. And then the second line corresponding to a constraint on which the point x star lies would be the budget constraint. And the budget constraint is 4x1 plus 5x2 is less than or equal to 2000. For printed fabric constraint, this tells us that x2 is equal to 300. And then we have 4 times x1 plus 5x2 is equal to 2000. And we plug in x2 equal to 300 into this second equation. From here we get 4x1 is equal to 500, meaning that x1 is equal to 125. So therefore we obtain the following optimal solution. So we have x1 star is given by 125, x2 star is 300, and when we plug in x1 star and x2 star in the objective, we obtain 9375. So z star is equal to 9375, and we are done. Alright, we solved our original heavenly pouch example. Now let's see what happens if we slightly modify it by raising the price of non-reversible carrier by $5. Alright, so the new objective now is 20 times x1 plus 25 times x2. Remember, it used to be 15 times x1 plus 25 times x2, but because we raised the price by $5, assuming it doesn't change the demand and everything else remains the same, only our objective changes. The objective function coefficient for x1 is going to increase from 15 to 20. Okay, now looking at this model, look, the feasible region is still the same as before, so that yellow region remains unchanged, but what will change will be the slope of the isoprofit line, because before the slope was defined by the coefficients 15 and 25, and now the coefficients are 20 and 25. So the slope is going to be different. So let's see how it affects the solution. Alright, so here we have the same feasible region as we expected, but now looking at the isoprofit line, we can actually see that it is parallel to one of the binding constraints at the point of the optima that we had. And the binding constraint would be the constraint that is satisfied at equality at the point that we are interested in. And the point that we are interested in is our optimal solution that we had before as optimal. And we can see it still remains optimal. Right, so but now because the isoprofit line is parallel to one of the constraints that define this optimal point, what is happening here is we obtain infinitely many optimal solutions now. Look, when we move the isoprofit line and we keep increasing the target profit, so the isoprofit line is going to move up, up, up. And then eventually we hit the border of the feasible region, and we can see that after this point we cannot increase the profit anymore and still have the feasible solutions that correspond to this profit. Therefore, this last point that we touch on the way out of the feasible region would be the optimal points. And we can see that we actually hit two corners at once on the way out, and both of these corners correspond to the same level of the objective, therefore both of them will be the optimal solutions. And not only these two corners will be optimal, but everything in between on this line segment between the two corners will also be optimal as well. So we have infinitely many optimal solutions. And looking even at this illustration, it becomes apparent that no matter which objective function we will have, when we try to move this isoprofit line, so let's say, let me try changing the slope to anything arbitrary here. So assume that we change our objective function, and now our isoprofit line becomes something like this. So if I move it up, then x star is going to be again our optimal point for this isoprofit line. If I select a different objective and my isoprofit line is like this, then look, neither x star nor x prime is optimal, because I can keep moving my isoprofit line higher, and I still have other feasible points for which I reach the target objective value. And the last point that I'm gonna touch in this case will be this corner right here. But clearly, no matter what slopes I try here, I will always hit some corners on the way out, okay? So that's why these corner points play a key role in linear optimization, because we can actually prove it for a fact that whenever we have an optimal solution for our LP, at least one of the optimal solutions that we'll have will be a corner point. So let's call it a corner point for now, but then a little later we'll discuss this a little more rigorously. This example here illustrates this scenario when we have infinitely many optimal solutions. And again, just by looking at this illustration, we can see that once I have two optimal solutions, I have infinitely many, because everything in between is also going to be optimal. And this is clear from the plot, but we can also prove it rigorously algebraically, so that, you know, your LP, whenever it has more than one optimal solution, there will be infinitely many optimal solutions. You cannot have just two optimal solutions and that's it, all right? So if it was an integer program where you have the integrality constraints, then you could have a situation where you have exactly two optimal solutions, but not for a linear program, where as soon as you have two, everything in between these two optimal solutions will also be optimal, and you will immediately have infinitely many optimal solutions. Okay, so let's consider another example of solving a two-variable LP graphically. And in this case, we'll talk about a minimization problem. So assume that we have a retail store that is planning an advertising campaign aiming to increase the number of customers visiting its physical location as well as its online store. So one option for the advertising campaign is to invest in magazine ads. And if the company invests $1,000 in magazine ads, this will attract 100 new customers to the store, as well as 500 new website visitors. All right, so then the other option would be to invest in online advertising. And each $1,000 invested in online advertising will attract 50 new local store customers and 1,000 new website visitors. Okay, so now the target of the campaign is to bring at least 500 new guests to the physical store and at least 5,000 new visitors to the online store. And of course, we want to achieve this target at a minimum cost. Okay, so we want to formulate the LP to help the store to minimize the cost of the advertising campaign, and then we want to solve this LP graphically. All right, so we can define the decision variables for this problem based on the decision options that we have here. So essentially, we need to decide how much money we are going to invest in the magazine ads and how much money we are going to invest in the online advertising. We can have two decision variables. So the first decision variable will be for thousands of dollars invested in the magazine ads, and then X2 will be thousands of dollars invested in online advertising. And then we can formulate the LP as follows. You want to minimize the total amount that you spend on the advertising campaign. And then if you look at the store visitors that the advertising campaign attracts, every $1,000 invested in the magazine advertising brings 100 new customers to the store, and every $1,000 invested in online ads brings 50 more customers to the store. So therefore, the total number of customers that we gain by using both advertising methods will be 100x1 plus 50x2, and we need to have at least 500 new customers. So this is our first constraint for the store visitors. And then the second constraint will be for the website visitors formulated in a similar fashion. And finally, we have the non-negativity. All right. Now, we formulated an LP model, and it was easy to formulate in this case. But now going back to the implicit assumptions of LP and trying to analyze which of them were reasonable, we may say that perhaps this model is not extremely realistic, right? And because, this linearity assumption in this case may not be extremely good, because look, if you invest $1,000 and the first $1,000 you invest may attract 100 visitors to the store, but then you will have the diminishing returns on the next $1,000 and so on. So the linearity assumption is quite a bit of a stretch in this case. Nevertheless, this model may still be somewhat useful to try to determine a reasonable advertising strategy. All right, so let's plot the constraints and let's see what we get for the optimal solution. When we plot the feasible region for our problem here, we can see that there are two lines corresponding to the store visitor constraints and website visitor constraints, and the points that are feasible with respect to these lines would be the points above both of them. So the feasible points are in the intersection of the half planes contained above these two lines, as well as to the right from x2 axis and above the x1 axis, because we also have non-negativity constraints. So this yellow feasible region is infinitely large, and of course realistically we would also need to have some upper bound on the budget, because essentially this model here assumes the possibility of the infinite budget, saying that you would spend as large of the amount of money as you want on advertising campaign. Perhaps you could go to infinity. I mean, if you were infinitely rich, that would have been possible, but it's not very realistic, right? So, but anyway, the points that are far away in that direction towards infinity are not of interest for our model to start with, because we are trying to minimize the budget here. So we don't care about the upper bound on our budget. So what we need to do is to really minimize the amount of money that we're going to spend on this advertising campaign. So we start with some ballpark figure of, let's say, $15,000 that we would spend on the advertising campaign. Then we can clearly see that with the budget this large, we would have plenty of options to distribute the funds between the two types of advertising, and we would reach our goal very easily with this budget. Since we can see that there are plenty of feasible options for 15,000, we try to see if we can reduce the budget and still reach our objective. Then this leads to a new ISO cost line for z equal to 10,000. Then we can see that we are moving down here, and this also shows the direction for the ISO cost line. So now if I try to look at the ISO cost line and how it moves, so let's say I started with 15,000 and now I'm moving down. So we keep going, and we keep reducing our budget. We are still within the feasible region. We can still reach our goal of bringing enough customers to the store and the website. And then eventually we reach this corner right here, and we can see that once you hit this corner, if you keep moving, then you will be completely outside of the feasible region, which means that you are being a little too greedy for your objectives in terms of attracting the customers. So therefore, you cannot go below this budget right here that corresponds to 20/3, which is $6,666.67. With this budget, you will be able to reach your objective, and the budget would be split evenly between the two types of advertising that you're considering. All right, so what this example shows here is that even though the feasible region is infinitely large, we can still find the optimal solution to our problem. And infinite feasible region doesn't mean that we will not have an optimal solution. All right. However, if we were maximizing with this model, so let's say everything is the same, the feasible region is all the same, but I change my objective from minimization to maximization, the fact that I have an infinite feasible region allows the possibility of having an infinite objective, right? So, and we see that if you are maximizing, then our objective would be to spend as much as possible, which wouldn't be a smart objective, right? But just to show the point that you could have an infinitely high solution, we can use this example right here, right? So what does it mean in practice? Typically that your objective is infinitely large when you're maximizing. It probably means that your model is not very good. It's either unreasonable or unrealistic. For example, in this case, you would want to essentially waste as much money as possible, which doesn't make any sense, right? But again, theoretically, it's possible to have an infinite solution. And usually if you are minimizing, this would mean that it would go to negative infinity in such a case. Or if you're maximizing, we are going to plus infinity. This means that you have an unbounded problem. All right, so for the problem to be unbounded, you have to have an unbounded feasible region so that you can go to infinity, right? So you have space to go towards the infinite objective. But the other way around, if let's say you have an unbounded feasible region, it doesn't mean that the problem will be unbounded. You can still have a finite optimal solution, and we will call the problem unbounded only when there is no finite optimal solution, and you can go to either negative infinity for minimization or to plus infinity for maximization. Another example is if, let's say, I had the limit of say $5,000 on my advertising budget, and I would say, okay, I want to minimize my budget, but at the same time I don't want to spend more than $5,000, right? So essentially I would add the constraint here that corresponds to these points below this line right here. Okay, so you have x1 plus x2 is less than or equal to 5. So when you have x1 plus x2 less than or equal to 5, then clearly you wouldn't have any intersection of these points with the points in the yellow region, and therefore you would have no feasible points at all. All right, so in this case we say that the problem is infeasible, and we cannot find a solution that would satisfy all of the constraints at once. Again, when you have an infeasible LP, it means that either you are being unrealistic with your model or something is wrong with the way you formulated it. Okay, so in this case, we are being unrealistic because we are trying to achieve unrealistic goals in terms of bringing the customers with the budget of $5,000. So clearly this is impossible. All right, even with these small two variable toy examples, we have seen enough to classify the LPs in terms of the types that we can have and the type of situations that we can encounter when we solve the general linear programs. So we have seen that the LPs can be either feasible or infeasible. So let me illustrate this classification with a decision tree essentially. So let's say here you have LPs, they can be either feasible or infeasible. So when we try to solve our LP, if we see that it is infeasible, then this is our conclusion. The problem is solved. This is the output of your solution process. The problem is infeasible. The model we are trying to solve is unrealistic. Something needs to be changed about it if you want to have a feasible solution. All right, so but if LP is feasible, then what can happen to it? So we have seen that in some cases we can have the optimal solutions, and we will call the LP that has at least one optimal solution an optimal LP. So this is one type that we get for feasible LPs. And we have also seen that, let's say in the example where we were trying to maximize the budget of advertising campaign instead of minimizing it, we saw that the problem can be unbounded because you could allocate infinite amount of money to the advertising campaign. You would reach your goal, right? So you would be just wasting money. So, but if this is your objective, then you can go to plus infinity, and therefore the problem is unbounded. So now with optimal LPs, we also saw that there is a possibility that you'll have a unique optimal solution, or you'll have infinitely many optimal solutions. So in this case, you have a unique optimum, or you could have infinitely many. So remember that situation where the isoprofit line was parallel to one of the binding constraints. We cannot have, let's say, just two optimal solutions, as we pointed out. So once you have two optimal solutions, there will be infinitely many optimal solutions. This concludes the video. Thank you for your attention.